We are looking at chapter number 15, which is waves. For the wave on a string, which is described in exercise 15.11, that is the question 15.11, do all the points on the string oscillate with the same frequency, phase, amplitude? You have to explain your answer. And what is the amplitude of a point this meter away from one end? The answer is something like this. Then we'll give the explanation first, then you will understand what is happening here. First is the all points or all the points on the string will oscillate with same frequency only at the nodes where the frequency is 0. So at the nodes the frequency will be 0. Otherwise all the points on the string are going to oscillate with the same frequency. Then the second thing which is being sought here is phase and then amplitude. So all the points in any vibrating loop, they have same phase only except the nodes. And third is all the points in any vibrating loop have different amplitudes of vibration. You can just check here. You just draw and you'll see that what is happening. At every point, this point amplitude is different, this point amplitude is different. Okay. Then the equation, this we got it from 15.11, the question or exercise. Here, if you put, because the question is given, what is the amplitude of point this meter away from one end? So we have to find the amplitude when x is this one, 0.375. So the given equation was this, yx comma t was this. So let us put this x as 0.375 and t equal to 0. So when we put t equal to 0, this becomes 0, cos 0 is 1. When we put x equal to 0.375 here, it becomes 0.25 pi, or cos 0 is of course 1. So we can find out the value. This is nothing but sin pi by 4, which is 1 by root 2. So 0.06 into 1 by root 2 is 0.042. Given below, these are some functions of x and t to represent the displacement. This is the displacement with respect to x and t. Now these are transverse as well as longitudinal. We have to state which of these represent a traveling wave and which of these are stationary wave, or none of these are either traveling wave or stationary wave. First one will come here. See, this equation represents a stationary wave. Why? Because the harmonics kx and omega t, this one and this one, means kx and omega t, they appear separately, and this is only possible when we are talking about stationary wave. In this case, y equal to 2 under root x minus vt. This equation has no harmonic form, so this is neither a traveling wave nor a stationary wave, so neither of them. And this one is our stationary wave. Now here we have y equal to 3 sin 5x minus 0.5t plus 4 cos 5x minus 0.5t. In this equation, this is representing a traveling wave because the kx, this one, and omega t, kx omega t, these are in the combination, means kx minus omega t. Here also it's kx minus omega t form. Here k is 5x, omega is 0.5. So this equation is a traveling wave equation. How about this one? Y equal to cos x sin t plus cos 2x sin 2t. This equation is a stationary wave. Why? Same discussion. Because the harmonic terms, this kx and omega t, they, in this also kx and omega t, they are occurring or they are appearing separately. This equation actually represents the superposition of these two stationary waves, this one and this one. A wire stretched between two rigid supports vibrates in its fundamental mode with a frequency of this much. This is the frequency. The mass of the wire is also given, and its linear mass density is also given. What is the speed of transverse waves on the string? Speed of transverse wave we have to find out, and the tension in the string we have to find out. So the mass of the wire is given this much. The linear mass density, which is, we know how to find this mu, which is mass per unit length, and this is given here, kg per meter. So this is also given here, mu is given here, and the frequency is also given 45. So frequency is given. Now how to find out the length? You can take length here and divide m by mu. So if you divide m by mu, mass is given to us, mu is also given to us. So mass by mu is your length, 0.875. This is the length of the wire. In this case, the wavelength of the stationary wave, which is lambda, is related to the length of the wire by what relation? In this particular case, we have lambda equal to 2L by n. What is n here? This is the number of nodes in the wire. So n, for fundamental node, we have to put n equal to 1. So when we put n equal to 1 in this equation, n equal to 1, what we get? Lambda n equal to 1, you get lambda equal to 2L. So lambda equal to 2L. Easily you can find out lambda because L is known to us. We just found out 2 into 0.875, which is 1.75 meter. Now, what is the speed? We know V equal to mu lambda. This is frequency, this is wavelength. Frequency is known to us, 45. Lambda also we just found out. Put it here. The speed is of the transverse wave is this much. We also know that V is given by under root T by mu. In order to find T, square this and multiply with this. So T is V, this mu square, V square mu. Velocity we have found out, mu we already know. Multiply these two, you get the tension produced in the string. A meter long tube open at one end with a movable piston at other end. It shows the resonance with a fixed frequency source, the tuning force of frequency this much, and the tube length this much or this much. Estimate the speed of sound in air at the temperature of the experiment. The edge effect may be neglected. How we are going to proceed with this? First is, we will write the frequency. This is the frequency of the tuning force. You see, this given pipe is attached with a piston at one end. So it is going to behave as a pipe with one end being closed because of this reason, and other with open end. So this will be closed and this side will be open, as you see here. And this kind of situation, we know, we have seen in theory that this will produce odd harmonics. This is going to produce odd harmonics. So what will be the fundamental node in this closed pipe, which is given by this L1 is given by what? Lambda by 4. We know about this. So L1 will be lambda by 4. L1 is given as 25.5. This is centimeter. Convert it into meter, and this lambda will be 4 into L1. This, see, L1 is lambda by 4. What will be lambda? Take 4 here. Lambda will be 4L1. So 4 into L1, L1 is this much. So 4 into 0.255, which is 1.02 meter. Now we can easily find out the speed also. Speed is frequency into wavelength. The frequency is given also, and the wavelength also we found out. Multiply these two, we get 346.8 meter per second. This is the speed of sound. Now a steel rod which is 100 centimeter long is clamped at its middle. The fundamental frequency of longitudinal vibration of the rod is given to be this much. What is the speed of sound in steel? First of all, the length is given as 100 centimeter, which is evaluated as 1 meter. This is 2.53 kilohertz. K is for 10 to the power 3. So this is 2.53 into 10 to the power 3 hertz. So when we have a rod, see, this is a rod which is clamped at the middle. This is clamped at the middle. That means here you will find that a node will be formed. So the fundamental mode of vibration of the rod, the node is formed at the middle, this point, and antinodes are found at the end. So what is the situation here? From here to here we know it is lambda by 4. From this point to this point it is lambda by 4. When you add these two, lambda by 4 from this point to this point, this is lambda by 4 plus lambda by 4, which is equal to lambda by 2. So L becomes lambda by 2. What will be lambda? L into 2. So lambda becomes 2L. And what is this length? 1 meter. Put length equal to 1 meter, you get 2 meter. Now we all know V equal to nu lambda. Nu is the frequency. We are going to use this frequency. Lambda we just found out 2. Put it here. Multiply them. This is the velocity. A pipe 20 centimeter long is closed at one end. With harmonic mode of the pipe is resonantly excited by 430 Hz source. Will the same source be in resonance with the pipe if both ends are open? The speed of sound in air has to be taken this much. See, the answer is, it should be first fundamental, the second part is no. How? Let us see. We'll write whatever is given to us. The length of the pipe is given to us, which is 20 centimeter. Length is 20 centimeter, so just divide it by 100, you get it in meter. What is the source frequency? The source frequency is simply the nth normal mode of frequency, that is, we call it as Vn. So the harmonic mode of the pipe is resonantly excited by this much frequency of the source, which is the source frequency, nth normal mode. So we can write it as Vn equal to 430 Hz. Now in a closed pipe, we know that the nth normal, this much normal mode of frequency is given by what? There is a relationship. Vn is given by 2n minus 1 V by 4L. This equation we know. Vn, as I said, we took it as 430. 2n minus 1, let it be like this. V is our speed, 340, and 4 is 4. Length is 0.2 meter. Put it here. We have to find n. I hope you'll be able to find n. N comes to be 1, near about 1. Now, the first mode of n equal to 1. So the first mode of vibration frequency is resonantly excited by the given source. This is not known to us. So in a pipe open at both ends, what will be the nth mode of vibration frequency? This also we know, we have seen in the theory that Vn is given by n into V by 2L. Basically it is equal to n V by 2L. So we have to find out this n. We take 2L here, divide by V. So 2L into Vn by V. This all we know. 2 we know. 0.2 we know because length is 0.2. This Vn is 430. And of course V is the 340. This is 0.5. So since the value n has come 0.5, which is equal to half, so the number, and we know that since the number of mode of observation n, it has to be an integer, this given source does not produce a resonant vibration in open pipe because half or 0.5 is not an integer. Two sitars, the sitar is a musical instrument, A and B playing the note Ga, Sa Re Ga Ma Pa Dha Ni Sa. So Ga is being played. These are slightly out of tune and they produce beats of frequency 6 Hz. The tension in the string A is slightly reduced and the beat frequency is found to reduce by 3 Hz. The original frequency of A is 324 Hz. What is the frequency of B? So here, the frequency of string A, FA, is 324 Hz. The frequency of string B, we don't know, we have to find it. But the beat frequency is given 6 Hz. See, it is given as 6 Hz. Now, we know how to formulate the beat frequency. Beat frequency is given by n equal to FA plus minus FB. That means n is the frequency, which is 6. So we'll use this. F is known to us 324 and plus minus FB. So once you will use plus sign, the next time you will use the minus sign. So what will be FB? One time it will be 330, the other time it will be 318. So 330 and 318 has come. Now, since we have to answer the other part also, the frequency decreases with decrease in the tension in a string. Why? Because the frequency is directly proportional to the square root of the tension. Frequency is directly proportional to the square of the tension. So frequency will decrease with decrease in the tension, frequency will increase with increase in tension. So V is directly proportional to under root T. That is why the beat frequency cannot be 330 Hz. So it has to be 318 Hz. This is the explanation. Explain why or how in a sound wave a displacement node is a pressure antinode and vice versa. See, a node is where the amplitude of vibration is minimum, like this. Like this. Okay. So this is a node, these are the antinodes. So here at this point, the amplitude of vibration is minimum and the pressure is maximum. Pressure is max. But if we talk about the antinode, these are the point. Here the amplitude of vibration is maximum. A is max here. And P is not max, but P is minimum. That is why in a sound wave, we can say that displacement node is nothing but a pressure node and vice versa. This is first explanation. Next is BAT can ascertain distances, directions, nature, sizes of the optical without even having eyes. We don't have the proper way, the vision we have. So BAT emits high frequency ultrasonic sound waves. They are capable of sending high frequency ultrasonic sound waves. So these waves, they are reflected back toward them by obstacles. Like if this is a bat, it sends the waves, and by obstructing, if there is any say body or obstacle, this will reach again back. So bat now receive the reflected wave, and now he or she estimates the distance, direction, nature and size of the obstacle with the help of its brain senses. Next is this one. A violin note and a sitar note may have the same frequency, but we can distinguish between the two notes. How? See, the overtones which are produced by sitar and violin and the strength of these overtones itself and the strength of overtones, these are different. So one can distinguish the notes produced by sitar and violin even if they have same frequency of vibration. And there is one more thing which is called timbre. Timbre helps us to differentiate the sound. Next is solid can support both longitudinal and transverse wave, but only longitudinal wave can propagate in gases. So the reason here, we'll try to answer this one, right? See, both these solids, they have shear modulus. What they have? Shear modulus. So they can sustain the shearing stress. Since these fluids, they do not have any different shape, they yield to shearing stress. When we are talking about the propagation of this transverse wave, the propagation of transverse wave is such that it will produce shearing stress in the medium, and the propagation of such wave is possible therefore in solid because they have shear modulus, but not in gases. Both solid and liquids, they have bulk modulus B respective. Now they can sustain the compressive stress. That is why the longitudinal waves here, they can propagate either in solids or in fluids. The shape of the pulse get distorted during propagation in a dispersive medium. So a pulse is what? This is nothing but a combination of waves having different lambda wavelength. These waves, they travel in dispersive medium with different velocities, and this depends on the nature of the medium also. So the result is the distortion of the shape of the wave pulse. A train standing at the outer signal of a railway station, it blows a whistle, and the whistle of frequency 400 Hz in still air. What is the frequency of the whistle for a platform observer when that train? First, it approaches the platform with this speed, recedes the platform with this speed, and what is the speed of sound in each case? The speed of sound in still air has to be taken 340 meter per second. So the idea here is frequency of whistle is V, 400 Hz, which is given in the question. Speed of sound we have to use 340, and the speed of train, this one, is 10 meter per second. So when the train is approaching the platform, that means the observer is at rest. We know the V dash, the apparent frequency will be V by V minus Vs into frequency. All these values are known to us, just put it here. You get 412 Hz. Now when the train recedes from the platform, that is the observer is now from the observer which is at rest, this gives you V by V plus Vs into frequency. So all these values are known to us. Put it here, we get 389 Hz. In the third one, what is the speed of sound in each case? See, the speed of sound in each case, it never changes. The speed will remain same. The frequency only changes. A train standing in a station yard, it blows a whistle of frequency this one. So this already we have seen. See, it's a kind of question which matches with the question here. So we'll take a look here because the formulation is somewhat different. So let us see. It is somewhat nearer to the previous one. So a train standing in a station yard, it blows a whistle with frequency this one. Now we have a wind here. So the wind starts blowing in the direction from the yard to the station with a speed of this much. So there is a wind speed also. What are the frequency, wavelength, speed of sound for an observer standing at the station's platform? Also, is the situation exactly identical to the case where the air is still and the observer runs towards the yard at a speed of this much? The speed of sound in still air, this can be taken this much. So this is the answer actually, and we'll see how we got this answer. You must remember these underlined values because we are going to use it directly. So the frequency of sound produced by the whistle is also given, speed of sound is given, velocity of wind is given. Now, there is no relative motion between the source and the observer. So the frequency of sound which is heard by the observer will be exactly same as that is being produced by the source. So it will be 400 Hz only. One thing is clear. Now there is a wind. So our wind is blowing towards the observer. The effective speed of sound will increase by what? 10 units because the wind is also there. We have to add it. So the effective speed VE will be 340 plus this 10. 10 is of wind. So this becomes 350. Now what will be the wavelength of the sound which is heard by the observer? We know the wavelength is given by this V effective by the frequency 350 by this frequency 400 Hz. This is 0.875 meter. And if we have a running observer, we know that the velocity of observer is given as 10 meter per second. Now the observer is moving where? It is moving towards the source. And because of this scenario, the relative motion of the source and the observer, there is a change in frequency. This V dash is given by V plus V0 by V into this frequency. So 340 plus 10 by 340 into 400, this gives you 411.76. And since the air is still here, the effective sound will be what? 340 plus 0, air is still here, it will be 340 meter per second. The source is at rest, so the wavelength of the sound is not going to change. Lambda will remain as 0.875. So these two given situations, they are not exactly identical, they are different. So these are the question and answer on this topic. Thank you so much and take care of yourself.